I'm going to get into a different kind of bonding. There's really three different kinds of bonding that we're going to describe in this particular unit. So I want to review the one that we've been focusing on up till now, and that is ionic bonding. So I've got a couple of the examples that I used in my previous video just to kind of recap some things. I don't think you'll have to write any of this because it should already be written down. But what I showed you last time was kind of a way of using diagrams to understand what happens during ionic bonding. So in this first example here, when barium wants to bond to chlorine, this takes place by the transfer of electrons from one atom to the other. So remember, there's always a metal atom involved that is trying to get rid of one or two or maybe three outer electrons. And by doing that, by losing those, it has a full outer energy level, because then the next energy level in is the outer energy level. So in order to get rid of the electrons, it's going to have to find something to take those electrons. And so that's where the non-metal atom comes in. Non-metals are just one, two, or maybe three electrons short of a full energy level, and so they will happily take some more electrons. So in the case of barium, trying to get rid of two, and we have a chlorine trying to acquire one more. So one of barium's electrons can go to this chlorine, and then that chlorine's happy. But barium still has a second electron to get rid of, so a second chlorine atom is necessary. And so then we've got one barium atom giving away electrons and two chlorine atoms accepting the electrons. And that's how we arrive at the formula for that particular compound, BaCl2. That's one barium bonding with two chlorines. Barium and phosphorus, a little bit more complicated, because phosphorus is not looking for one, but it's looking for three additional electrons. It's in group 15, which means it has 5 outer electrons, which means it's just 3 short of being full. Well, barium doesn't have 3 to give away, so it's going to take multiple barium atoms to make phosphorus happy. So 2 from one atom, and then it can take 1 more from a second atom. Well, then we've got a barium kind of half happy, and so it's going to give the other electron away to a second phosphorus, and then we need yet a third barium atom to give away 2 more electrons. So 3 barium atoms and 2 phosphorus atoms are enough to make all 5 of them happy. So we write the formula Ba3P2. Okay? So the transfer of electrons, that's what ionic bonding is. So now let's look at what happens with the other kind of bonding, what we call covalent bonding. So now you can write some new information down. So in covalent bonding, instead of transferring, remember ionic was transferring electrons, from one atom to another, so in covalent, the electrons are shared by 2 atoms. Okay? So think about what it takes to share something. You're going to have to be close to each other, so that the thing that's being shared can be claimed by both at the same time. Okay? So we can write this too. Atoms are close to each other and you can think of it this way. They sort of overlap their outer energy levels. Okay, so the key word here is shared. Okay, so sometimes we just summarize it saying When you share electrons, that's covalent bonding, and when you transfer electrons, that's ionic bonding. Okay? Draw a little picture here just to kind of demonstrate what we mean by this sharing. So I don't want you to draw this because it would be an awful lot, but just kind of pay attention as I describe what's happening here. If we want to do a compound made of silicon and hydrogen, okay? So silicon is element number 14. You could look it up on the periodic table, which means it has 14 protons in the nucleus, but it also normally has 14 electrons in its energy levels. So let's think about where those are going to be. We'd have 2 in the first energy level, because that's all it can hold. And then the second energy level can hold 8. So I'll put 2 here, 2 here. And rather than spread them around, I'm going to kind of pair them up in the sides and top and bottom. That makes 10. So now we need 4 more. So suppose we have 1, 2, 3, 4. Now I put those there for a reason. You see how they're kind of close to the hydrogens? So let's talk about the hydrogen's electrons. Hydrogen is element number 1. It has exactly 1 proton and exactly 1 electron. So it only has 1 energy level. So I've drawn its nucleus here and then 1 energy level. So suppose that hydrogen positions that outer energy level, that outer electron, to be next to silicon's outer energy level. Now remember we call the outer energy level the valence level. That's where we get the term covalent. Co meaning together, and valent referring to the valence energy level. So we've kind of overlapped them, and so if we count now how many outer electrons each atom has, watch this little trick. We go around silicon here, around this big circle. We're going to count silicon's 4 electrons, plus we're going to count the ones that it's sharing with hydrogen. So that's 1, 2, 3, 4, 5, 6, 7, 8, which is perfect. That's how many it wants. And how many does hydrogen have? Now remember, hydrogen's kind of special. It only has 1 energy level, and it can't hold 8, so it's only looking for 2. Each hydrogen has its own electron, the green one, and then the purple one that also is being shared with silicon. So there's 2 for that hydrogen, 2 for this hydrogen, 2 for this hydrogen, and 2 for this. So we've got 5 atoms, and each one can claim a share of all the electrons to say it has a full outer energy level. Okay? So I'm not going to expect you to be able to draw things like this, but I want you to recognize an arrangement that has a proper sharing of electrons. Okay? So I'll show you an example, and that's the ones that I'll have you do for practice. So what kind of diagrams would be correct diagrams to show the sharing of electrons in covalent bonding? Let's take a look at those next. So someday you may take a chemistry class where your teacher will expect you to draw these yourself, but I think in this class I'm just going to have you recognize when a drawing is correct or not, so you can pick out one that works from ones that don't work. So there are 2 requirements to know if you have a correct diagram for a covalent bonding. Here's the requirements. Must, and here they are, have all outer electrons from all atoms involved. Okay, I'll show you what this means. I'm just going to write it for now. And they must have 8 electrons around all atoms. Except for hydrogen, which, as I was just showing you, it's satisfied with 2, not 8. Okay? So I'll show you a couple examples, one that is a good diagram and one that's not so good. Okay, so let's look at what we mean by have all outer electrons from all atoms involved. Okay? So I will always give you the formula for the compound that we're talking about. In this case, PCl3. It's got the fancy name phosphorus trichloride. All you need to know is that there should be 1 phosphorus and 3 chlorines. We kind of worked on that when we did the other kind of bonding. So you need to know how many total outer electrons those 4 atoms should have. So you look up on the periodic table that phosphorus is in group 15. It should have 5. And each chlorine, being in group 17, should have 7. So that's 5, 7, 7, and 7. That's a total of 26 electrons. So your diagram must have 26, all right? So if you count around this one, I made some of them dots and I made some of them little X's just so you could kind of tell them apart. There are a total of 26 around there, okay? On some of these incorrect ones, for example, down here, you will notice there's only 24 down here. That cannot be the correct diagram for that particular compound. On this one, there are 26, so this one's okay. But there's another requirement, I'll remind you. They must have 8 electrons around each of the atoms, okay? So when you look at each of the 4 atoms in here and you look around it, make sure you can count exactly 8, not 7, not 9, but exactly 8. So around this chlorine up here, if I draw a circle around it, I can see 8 around there, kind of 2 on each side. Around this chlorine here, same thing. It's got 7 of its own, but it's got this one here from phosphorus. That makes 8 for it. There's also 8 around this chlorine. And then if we look at the phosphorus, it's got 2 on each side as well. That's a total of 8 for it. So we've had a clever way of taking 26 electrons and putting them in a position where all 4 atoms can have a share of 8. All right? So on this one here, the chlorines have a share of 8, but the phosphorus, if you count, only has 1, 2, 3, 4, 5, 6 around it. That's why it is not a correct diagram. And on this one here, we've got the correct number of electrons, but if you look around the chlorine here, there are 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 electrons. That's not the right number. And if you look around the phosphorus, it's got 1, 2, 3, 4, 5, 6, 7, 8. It looks like it's okay. Except this chlorine right here is the one that kind of causes us the problem. All right? So we can't have 9 there and have it be a correct diagram. All right? So when I show you examples to choose from, I want you to check for both things. All the electrons are accounted for. That's just a counting process. And each and every atom must have exactly 8 around it. No more and no less, right? Again, except for the case of that hydrogen where we can have just 2 because hydrogen doesn't have room for 8. It's only got a single energy level, and that energy level can hold 2. All right? Let me do one more example, and then I'll stop here, and you make sure you got all the notes down, and then I'll give you a chance later on the worksheet to apply what you saw. So let's look at an example of how we make a compound with 2 sulfur atoms. Okay, when we can have 2 of the same kind of element combined when we do covalent bonding. But that could not happen with ionic bonding because you need a metal combined with a nonmetal. So covalent is great when we have 2 nonmetals bonding together. All right, so let's look at these 3 different diagrams and let's just run that check. Do they satisfy both requirements? Do they have all the outer electrons accounted for? And are they showing that 8 electrons are around each and every atom in there? So first we have to know something about sulfur. So you should be able to look up sulfur on the periodic table and see that it is in column 16, group 16. That means it has exactly 6 outer electrons. So if we've got 2 atoms and they each have 6 outer electrons, our diagram must show 12 total electrons. What does this first one here show? Counting kind of over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Not the correct number. I've got too many electrons in here. So that one can't be a proper diagram. What about this next one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's got the right number of atoms. This one down here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So those 2 are okay. But now let's do the other test. Do we have 8 electrons around each and every atom in the compound? Well, around this sulfur atom here, we just kind of imagine a circle around it. I wouldn't want to draw it, but we could count 1, 2, 3, 4, 5, 6. And around the sulfur atom here in purple, 1, 2, 3, 4, 5, 6, 7, 8. So the purple one's happy, but the sulfur over here on the left does not look like it has enough. So that one does not count as a correct diagram. So this is the only one that's correct, because if you put a circle around it, and I think I'll actually do that very lightly, just so you can see how I'm counting here. Around this sulfur atom, you see how it has a share in all 8 of those, because the 2 over here are positioned next to both of them, kind of in between them. So if they're being shared, they should be drawn in between them. The sulfur here gets to also count those in between them as being shared. So these 4 are really claimed by both of the atoms, plus 4 of its own. So now we have 8 around each. So we got the right number, 12, and we've got 8 around each, so that's the right number being shared, and so we've got a correct diagram. So we would say, yes, that is a correct diagram for that, okay? All right, so let me do one more quick thing, and then we'll call that a wrap. You can make sure your notes are correct, and then we'll move on and apply it in the next class. So I'm going to have you write something that I mentioned, but I hadn't written before. And you notice when we do covalent bonding, each atom actually acquires more electrons because it's got its own still, but it's also got some more that's being shared from another atom. So think about the kinds of elements that are going to want to acquire more electrons. The only ones that do that are the nonmetals. So covalent bonding is how nonmetals bond to other nonmetals. Okay, so anything on that right side of the periodic table, to the right of the stair-step line, any atoms in there bonding to each other, that could be nitrogen with oxygen, it could be, let's say, chlorine with another chlorine, it can even be the same element like that. That would be a covalent bond, not an ionic bond, because ionic, you need a metal with a nonmetal, okay? All right. The other thing I want you to know is the resulting compound is called a molecule. You've heard that term before. Pause if you need to write that, but I want to show you what we mean by this. So when we had the 2 sulfur atoms, we would say that is a molecule of S2. And when we had the silicon with the 4 hydrogens, this is a molecule of silicon with 4 hydrogens. Or my example here, PCl3, that's a molecule, okay? We don't have molecules with ionic bonding, but we do have that with covalent bonding, all right? So make sure you get those ideas down there, and then we'll call this good for now. And like I said, we'll apply this a little bit later. Let me know if you have any questions about that.